At 37,000 feet, a Boeing 747 is held in the sky by 4 engines. On the night of June 24, 1982, all 4 stopped, not at once, but one after another, until British Airways Flight 9 had no thrust at all. The passengers could still hear air rushing over the fuselage. The cockpit instruments were still alive, but the deep vibration that defined the aircraft was gone. A jet weighing hundreds of tons had become a glider above the dark sea south of Java. There had been no collision, no fuel shortage, no storm on the radar, and the crew did not yet know what had taken their engines. To survive, they had to solve an invisible failure, while a LTITUDE Chinese letter, HE only energy, they had LEFT Chinese letter, OUNTED down beneath them. This is not only a story about excellent flying. It is a story about a hazard that could reach every engine through the same path, and about the narrow sequence of events that let the aircraft escape. Flight 9 was operating the Kuala Lumpur to Perth leg of a longer service from London to Auckland. The aircraft, a British Airways 747-200, was cruising through clear night conditions near the island of Java. Ahead and to the east, Mount Galunggung was erupting, but the flight crew had not received a useful warning, and the cloud in their path did not announce itself like a thunderstorm. Airborne weather radar is designed mainly to show moisture. A dry cloud of fine rock and glass can be extensive, yet return little of the signal a crew expects from dangerous weather. In darkness, its boundary may be almost impossible to see. So the aircraft crossed into volcanic ash without a red cell on the radar and without a wall of cloud visible through the windscreen. That is the first link in the Cascade. A major environmental hazard existed, but the systems available to the crew did not turn it into an actionable picture. The aircraft was already inside before anyone knew there was something to avoid. The first signs were strange rather than conclusive. A blue-white electrical glow flickered across the windscreen. St. Elmo's fire, created when charged particles intensify the electric field around an aircraft. The engine inlets appeared to glow. A dry haze and an acrid electrical smell spread through the cabin. Fine material was striking and abrading the aircraft, but none of the individual clues came with a label saying volcanic ash. To a crew in 1982, these symptoms did not form a familiar checklist. Then the engines began to surge. Their airflow was becoming unstable. One engine lost thrust, then another. The failure moved across an architecture designed around redundancy. 4 engines normally mean that one engine problem does not become an aircraft problem, but redundancy only protects against failures that remain independent. Here, every engine was breathing the same contaminated air. The shared atmosphere had become a hidden connection between systems that appeared separate on the engineering diagram. Within minutes, the last engine flamed out. Redundancy had been defeated by a common cause. With no engines producing thrust, the crew lowered the nose to preserve flying speed. That distinction matters. An engine-out airliner does not simply fall. Its wings can still trade altitude for forward motion, but the exchange is irreversible. Every 1,000 feet spent buys a limited amount of distance and time. The crew turned toward Jakarta and began repeated restart attempts. At the same time, the loss of engine power affected more than propulsion. Aircraft's pressurization could no longer be maintained normally, forcing a descent toward breathable air. The pilots now had several clocks running at once: altitude, distance to a runway, terrain ahead, cabin pressure, and the time required for each restart cycle. Radio communication added friction. Air traffic control initially understood that engine number 4 had failed, not that all 4 engines had failed. The extraordinary message did not fit the listener's expectation. That misunderstanding was corrected, but it exposed another weak link. Even accurate information can fail when it describes a situation nobody expects to be possible. From cruise altitude, Flight 9 descended roughly 25,000 feet. ICAO training material describes about 16 minutes between the high-altitude encounter and the lower level, where sustained restart became possible. During those minutes, the crew kept the aircraft within a safe speed range and continued the restart procedure. The decision space narrowed with every rotation of the altimeter. Jakarta offered a runway, but reaching it required enough height to cross terrain and position for an approach. If the aircraft became too low before power returned, the safer option might have been to remain over water rather than commit to land it could not clear. There was no single dramatic control input that solved the problem. Survival depended on disciplined repetition: maintain the glide, monitor the descent, attempt a restart, assess the result, and do it again. This is what good emergency performance often looks like: not certainty, a sequence of small, correct actions that keeps one more option open. As the aircraft approached roughly 12 to 13,000 feet, that persistence finally met a change in the environment. To understand the failure, follow one ash particle through the engine. Volcanic ash is not soft smoke. It contains hard mineral and glass fragments. At the front of the aircraft, those particles sandblast the windscreen, lights, leading edges, and sensors. Inside an engine, the compressor raises the pressure of the incoming air. Fuel is added and burned in the combustor, where temperatures can exceed the melting point of the silicate material in the ash. The particles soften or melt. Farther downstream, they reach cooler turbine components and can stick to them as a glass-like deposit. That changes the carefully designed passages through which hot gas must flow. At the same time, abrasive particles damage compressor surfaces and disturb the smooth movement of air. The engine begins to surge. Airflow and combustion can no longer remain stable, and the flame goes out. Each engine on Flight 9 was separate mechanically, but each inhaled the same plume. The ash therefore acted as a common mode input: one external condition, four parallel failures. It is the kind of pathway conventional redundancy can miss, because adding another identical component also adds another component exposed to the same cause. Then, after repeated attempts, an engine restarted. Others followed. The most likely explanation is not that the ash became harmless, but that the aircraft had left the densest part of the plume and descended into cooler air. With no combustion, engine temperatures had fallen. Deposits could cool, become brittle, and break away as the rotating machinery and airflow changed. A restart could once again establish stable compression and flame. Eventually, all four engines produced power, though one later surged and was shut down, leaving three for the diversion. This outcome can sound like a built-in self-repair mechanism. It was not. Ash damage can be severe, restart may fail, and re-entering contamination can remove an engine again. The crew had found a narrow physical window in which the engine could operate despite what had happened to it. Their repeated restart attempts mattered because the conditions were changing while they tried. But the lesson for modern flight crews is not to wait for an ash cloud to clean an engine. It is to avoid the cloud, exit it quickly if encountered, reduce exposure, and report what happened so other aircraft do not enter the same invisible space. Power solved only the first emergency. The aircraft still had to land. Ash had abraded the windscreen so badly that forward visibility was severely reduced. Surfaces, lights, probes, and all four engines had been exposed. The crew diverted to Jakarta's Halim Airport and prepared an approach on three engines. With the outside world turned into a pale, scratched blur, they relied heavily on the instruments to align the aircraft with the runway. The final minutes demanded a different kind of discipline from the glide. Trust the indications, hold the approach, and resist the urge to search for visual information the damaged glass could no longer provide. Flight 9 touched down safely. Everyone aboard survived. Only after landing could the full pattern be seen on the aircraft itself: the polished, sandblasted exterior, the opaque windscreen, and engines contaminated by material that had passed invisibly through the night sky. What had looked in flight like several unrelated anomalies was, on the ground, one coherent chain written across the machine. There is an important limit to any reconstruction of Flight 9. Aviation references note that no independent investigation report under the modern Annex 13 model was published for the occurrence. Some familiar details come from crew accounts and later reporting rather than a single definitive report. But the central engineering lesson is not in doubt. Volcanic ash can be invisible to crews, difficult for airborne weather radar to identify, damaging to airframes, and capable of disabling several engines through one common exposure. Flight 9 became a landmark warning, and later encounters reinforced it. Today, 9 volcanic ash advisory centers divide responsibility for monitoring and forecasting ash around the world. Pilots and dispatchers receive dedicated advisories. Reports from aircraft, satellites, volcano observatories, and atmospheric models are combined to keep routes away from contaminated air. The system is still imperfect because volcanoes and winds do not respect aviation boundaries, but the hazard now has a name, an information chain, and organizations responsible for making it visible. Flight 9 survived because the crew preserved options long enough for the physics to change. Aviation became safer when the wider system learned not to depend on that luck. One fault, every consequence. This is fault cascade.